You ever find yourself standing in the kitchen just staring at the kettle, absolutely convinced it's taking longer to boil today than it did yesterday? We've all been there. Well, we're going to take that super simple, everyday feeling and use it to unlock one of the most powerful tools humanity has ever come up with.
So, let's get right to it. Here's the question. Does the amount of water you put in a kettle actually change how long it takes to boil? I mean, it feels like it should, right? But how do we know for sure? To figure that out, you need a system, a reliable recipe for finding the truth.
And that recipe is the scientific method. Now, don't let that name scare you off. It's not just for people in white lab coats. Seriously, think of it more like a step-by-step guide that anyone, and I mean anyone, can use to get real answers about the world around them.
And here's our roadmap. There are 5 basic steps. It all starts with just noticing something and asking a question. Then, you make an educated guess, you come up with a fair way to test it, you look at the results, and finally, you figure out what it all means. So let's put our kettle problem through this exact process.
Okay, step 2 is making a hypothesis. That's really just a fancy way of saying an educated guess. But the key is that it has to be something you can actually test. For us, it's pretty straightforward. A hypothesis is that more water will take longer to boil. It makes sense, but in science, we don't just go with what makes sense. We have to prove it. So, time to experiment. We run a fair test. We time how long it takes to boil a small amount of water, say 500 milliliters. Then we time a large amount, 1.5 liters, making sure everything else, like the kettle and the power source, stays exactly the same. And the results? Whoa, not even close. The small amount is done in a minute and a half. The large amount, it takes a full 4 minutes and 15 seconds.
And that brings us to our conclusion. The numbers are telling a really clear story here, no question about it. Our experiment completely backs up our hypothesis. We can now say with a whole lot of confidence, yes, more water takes way longer to boil. Our guess was spot on.
So our little kitchen experiment worked perfectly. But that's just the start. This exact same method is the engine that drives huge, world-changing discoveries. Let's zoom out a bit and see how this whole thing works in the big leagues.
You know, in the world of real science, you don't just get to do an experiment and declare you're right. No way! You have to submit your work to something called peer review. This is where other experts in your field try to poke holes in your work. They check your math, question your methods, and challenge your conclusions. It can be a tough process for sure, but it's what keeps science honest and makes the results so reliable. It's like the ultimate quality control.
Of course, you can't do every experiment in a lab. I mean, we could control the amount of water in our kettle, no problem. But what if you're an astronomer studying a distant star? You can't exactly put a star in a beaker. That's where observational studies come in. You're still testing a hypothesis, but you're doing it by carefully observing the universe and looking for patterns. The method's the same, it's just on a much, much bigger scale.
Okay, but what happens when you're wrong? This is where the scientific method gets really cool, because it's not just about proving you're right. Actually, some of the biggest breakthroughs in history have happened because an experiment showed that the original idea was completely wrong.
Just imagine this for a second. What if we ran our kettle experiment 10 more times, and on one of those times, the full kettle actually boiled faster? That would be weird, right? It would totally contradict our conclusion. So does that mean the whole scientific method is broken? Absolutely not. It just means our guess was too simple.
A surprising result like that forces you to think harder. It's a clue that we missed something. Maybe our first hypothesis, that only the amount of water mattered, wasn't the whole story. So we refine it. Our new, smarter hypothesis might be that boiling time depends on the amount of water and the power coming from the electrical adapter. See, we didn't fail. We just got more precise.
And that is the real beauty of this whole process. It's not a straight line. It's a cycle. You question, you test, and you refine your ideas over and over again. Every single result, whether it's what you expected or a total surprise, adds another piece to the puzzle. It gets us one step closer to really understanding how things work.
So after all of this, all the testing and retesting and arguing with peers and refining ideas for years, where does it all end up? Well, it leads to one of the most important and probably one of the most misunderstood words in all of science.
A scientific theory.
Now, let's be crystal clear about this. When a scientist talks about a theory, they are not talking about just a guess or a hunch. A scientific theory is a huge, powerful explanation for a whole range of things we see in nature, and it's been tested again and again and again and has held up every single time. It's the absolute gold standard. It's the best explanation we have.
So you see, from a simple boiling kettle all the way to the grandest theories about the cosmos, the fundamental process is exactly the same. It's a way of thinking that is available to every single one of us. Because when you boil it all down, all you really need are three things: a question, a guess, and a way to test it. So, what are you going to figure out next?